Good morning, good afternoon, and good evening. I'm your host, Aya Takase, and I am here with our presenters. So we have our co-presenter, Simon Bates. He will be facilitating the Q&A sessions. And we have Angela Criswell and Suzanne Schreyer as our speakers today. Thank you for joining our webinar series, Enhancing Pharma Processes with X-ray, Thermal, and Raman Analysis Tools. In this webinar series, we will discuss various practical analytical techniques and their applications to enhance pharmaceutical research and quality control. The episodes are organized by the different stages of research and production, and in this fourth episode, we will cover manufacturing and QC. But before we start, a few housekeeping items. This is going to be an interactive session, and I will be posting relevant links in the chat window, and we'll be taking your questions live during the webcast and answering them during the session, so please do not wait until the end to ask. Please submit those questions via the Q&A button at the bottom of your screen. We will not be monitoring the raise the hand function. We will try to answer as many questions as we can during the webinar, and we will respond to any unanswered questions by directly contacting you after the session is complete. If for whatever reason you have difficulty viewing the webinar live, please note it is being recorded, and you'll be able to view the recording beginning tomorrow. Now, with that said, I'm gonna hand this over to Simon.
Thank you, Aya, and greetings, everybody. Welcome, and thank you for attending our webinar today. Before starting, let me take a few moments to set the stage for our webinar series, tracing the drug product life cycle from discovery all the way through to drug product manufacturing and beyond. Today, we find ourselves in manufacturing in QC, and to start us off today, Angela will enlighten us on the use of X-ray CT for drug product QC. Angela.
Thank you so much, Simon. There we go. Okay. So as Simon mentioned today, we're going to be talking about characterization and quality control of pharmaceutical products using X-ray computed tomography. So let's get started. We're going to open first with a polling question for you in the audience.
Okay, so let me start the polling question. So the question that Angela had for the audience is, do you currently use X-ray CT to characterize your pharmaceutical samples? And here are your choices. Yes, I use X-ray CT extensively to characterize my samples. Or you might say, I use X-ray CT occasionally to address specific questions. Or I don't use X-ray CT, but I am considering integrating the technique. Or I don't use X-ray CT and don't plan to do so. Okay. I'm gonna give everybody a few more seconds to think about it. Okay. I think most of you answered the question. Okay, so I'm gonna close the poll in 3, 2, and 1. And let me share the results. Okay, so 50% of the audience said that they don't use CT, but they're considering it. And 29% said that they don't use it and they don't plan to.
Okay.
Okay, thank you. I'm gonna stop sharing and back to you, Angela.
All right, thanks so much. So hopefully by the time we finish today, we'll give you some more information. And for those of you who are considering it, you might see some areas where it can help you in particular. Okay, so let's get started. Specifically today, what we'll talk about is first we'll start with a brief overview of X-ray CT. Then we'll talk about how quantitative information is extracted from CT images. We'll look at an example of excipient and tablet characterization. And then we'll ask the question, how are devices characterized? Because they're characterized slightly differently than, let's say, the excipient and tablet characterization example. So let's start with that brief overview. So of course, to do this experiment, we need an X-ray source and we need an X-ray detector. And you have a sample of interest that's sitting here between those two. Once we turn on X-rays, some of the X-rays are absorbed by your sample of interest, but some make it through and are transmitted and measured on the detector in what we call a projection image. So during this experiment, what we do is we rotate the sample anywhere from between 180 and 360 degrees, and we output these 2D projection images at angular increments. And this in itself, we call a CT scan, and is the experimental portion of X-ray CT. From there, we end up with hundreds to thousands of projection images. And what we do is we put them into a program that will reconstruct the three-dimensional image. And then we end up with what we see here, and this is our output 3D data, or 3D volume image, we sometimes call it. And you'll see that it looks exactly like what we imaged. So there is here a tablet that's located inside of a tube with some foam, and we can see the tablet. It's a little bit of foam in this tube. So how is that relevant for typical pharmaceutical products? So pharmaceutical products have different types of dosages. Of course, we're very familiar with the solid dosage form. There are also liquid and cream or gel type forms. And finally, there are gas dosage forms. And it turns out all of these are fully accessible for interrogation by X-ray CT. But today, we're going to focus on a couple of examples, starting with solid form in that case. So let's dive briefly into that. So when we're looking at solid dosage forms, we start with a powder that contains an active pharmaceutical ingredient and an excipient. And then from there, this powder is mixed. During mixing, the tablet components are blended with the goal of ensuring that the API is evenly distributed throughout the mixture. And that ensures that every tablet has the correct dosage of the API. And CT is used at this step to characterize the API distribution and to characterize particles in the mixture. Next comes granulation, and this is a process that can be done either wet or dry, you may have heard. And the goal here is to create granules that contain both the API and the excipient, and CT is used to characterize granule shape and size. And those properties are important because they affect the flow properties of the mixture and can inform us whether or not the powder can be pressed into tablets without issues. And during tablet pressing, the mixture is fed into a tablet press and under pressure to form solid tablets. X-ray CT scans at this state give us insight into the API distribution, and it reveals any internal effects that may have happened during tableting. If we identify any tablet defects, then we can use that to help guide the upstream process to optimize these steps and our mixtures in that case. Following this, many tablets are then coated. This makes them easier to swallow, can help improve their taste, and it can also control how the drug is released in the body. So, for example, enteric coatings prevent dissolution in the stomach and instead ensure gastrodissolution. And X-ray CT, of course, is important at this phase to evaluate that coating thickness. Then finally, those tablets are packaged. And of course, CT is important here for quality control, to ensure proper sealing, and to identify defects. So CT runs across all of the gamut of these different processes, and it has some benefits. And the most notable one that we usually talk about is that it's non-destructive, and there's minimal sample preparation required. You'll remember that example I showed you with the tablet image. We just stick it inside of a tube with some foam to keep it from moving around during the scan. And ideally, at the end of the day, what we end up with is an exact digital twin of the sample. That's not always the case. We can have some artifacts, but generally after some time working with this technique, you start to understand how to minimize those. Also, with the advent of faster computers and programs, the analysis of CT images can be very quantitative. And even now, more emerging techniques, let's say, for example, artificial intelligence, computational tools that allow simulation, are making X-ray CT even more powerful. But I mentioned we have to get the quantitative information out. So how do we actually extract that stuff? So what I'm going to show you how we do this in one case is we have this 3D volume of an excipient material. So it's a two-phase, and here's just the block that was imaged. It has the excipient material and void. So if we take a look at a single 2D cross-section through here, then we see this. So we can see one phase is the excipient material and one phase is the void in between. If we look at a grayscale histogram of this data, there should be only a couple of peaks corresponding to those. We could very simply say, I'm going to draw a line at this point. Anything that is above this intensity is the excipient material, and anything below is the void space. And that's very quick and easy to do. In seconds, you can essentially segment or assign each voxel to excipient or void. And that's important because there are sometimes hundreds of millions to billions of voxels in a single three-dimensional image. But that doesn't always work. We have to resort to other tools. And how do we do that? So here's an omeprazole tablet, 3D volume data. If we cut through and look at a slice of this, we see something much more complex. So in addition to the background around it, we have a coating, we have granules inside and some matrix, even some cracks in this case. So how are we going to segment or assign voxels at each of these phases? Well, we're going to take advantage of artificial intelligence. And there are a number of products or software products that are out there that allow us to do what we call deep learning segmentation. It's pretty simple. What we do is we just identify a few different phases of the material, and we assign those either as background or matrix or coding and et cetera. We put this into the program, and it outputs a model that will characterize each of the different phases. And this particular example I showed here was segmented using Dragonfly. So once you've done this, then you can break your three-dimensional volume into the separate parts, and you can ask questions about the volume that is assigned to these various phases. So for example, the coding is 6.8% of the tablet, the matrix is over 66%, and granules right around 27%. So then you can ask questions, for example, I would like to understand the volume thickness of the tablet coating. So we can calculate the thickness, and then we get this color-coded or heat map that tells us the largest thickness is around 159, and we can highlight those as a sort of yellow color, and things in between as they get thinner, they're green to blue to purple. We can also ask questions, for example, about the granules. What's their volume percentage? If we want to ask questions about distributions among the granules, we can separate each of them into independent granules and then ask what's the distribution of the volume and how do they vary, and we can, of course, color code those. We can ask what's the sphericity of the granules. We can ask what's the equivalent spherical diameter of the granules. There's a number of different things we can ask that may be important for us to understand the process of how these tablets are made. So that's the primary way in which we are quantifying information for things like tablets and solid forms. So before we move on, I want to stop and allow you to ask any questions you might have.
Yes, Angela, we have a couple of questions. The first one is, can you look at more than one tablet at the same time?
Absolutely. There are different ways in which you can do that. For example, sometimes you can just image the entire bottle and image them all at one time. You can also just space them separately apart. There are also sample changers. So if it's important to you to image just a couple at a time, then our instruments have sample changes that we'll mount the sample, image it, put it back, and exchange it for the next one. So there are lots of ways that you can do that.
Okay, that's great. Thanks. And another quick question is back on slide 21, you gave some quantitative numbers for, I guess it's volume percentage for coating, matrix, and things like that. I mean, how accurate are those numbers?
It's a good question. So it's obviously only going to be as accurate as the assignments of the various phases. So there are points at which along the way during that segmentation process that you need to evaluate, and you also have to have controls in place to make sure that it's working properly to assign volumes properly. But at that point, of course, you can compare that to known characteristics, and that's been done and cited in the literature, and they come up pretty good.
That's great. Thank you.
Okay, so let's move on to our first example, and in this case, we're going to look at excipient and tablet characterization. So here, we're going to compare two different mixtures. So one mixture is a direct mixture of excipients and API. So we essentially, in a single powder, mix the API with all of the other ingredients. That may be some fillers, some disintegrant, and some binder. That's blended together to make a first blend. Before you tablet, you generally add a lubricant to encourage that powder to flow. That is blended into the final blend. From there, you compress into the tablets. And in this case, you'll see there's lots of steps with this. And a company called BASF has improved on that to co-produce excipients. And in that case, what they do is they create this mixture called Colatab that has fillers, disintegrants, binders, and lubricant. And you mix this directly with your active pharmaceutical ingredient to produce a blend. And from there, you directly compress into tablets. So what we did is we worked with BASF and a company called Natoli, and we looked at both the mixtures of each as well as tablets produced from each of these mixtures. So let's look at what just the powder looks like in that case. So these are two 3D volumes. We're diving through the 3D cross sections of the direct mixture, and we see that here on the left, and the Colatab mixture on the right. And as I'm looking at this right after collecting data, I'm noticing some characteristics that are different in them, and I'm making predictions about what may happen later on. So let's just look at that. Well, look at the direct mixture, we see that there are greatly different particle sizes. There are small particles and very large particles. Additionally, there are some particles that are filled and some that are empty. And we also see these, the API in this case, which is ibuprofen. If we compare that to the Colatab side, what we see is that most of the particles are filled. And even though there is a size distribution, it's much tighter than over on the left with these mixture of different sizes. It's more uniform. And just by eye, what I see is it appears to me that the porosity or the void space amount is different between the two. And in fact, if we calculate that from the data after doing segmentation, we see that that is in fact correct. The porosity in the case for the direct mixture is 49.4%, and for the Colatab mixture is 46.2%. After delivering this powder to Natoli, they produce some tablets with each of these. And on the left, we see the direct mixture, and on the right, we see tablets that were made from the Colatab mixture. And we received 10 of these tablets, and both of these images are pretty indicative of the group. They all of the direct mixture tablets have cracks throughout them, and they also have voids, sometimes quite large voids, especially near the outside. Now, let's just zoom in here to take a closer look. Now, I see that the Colatab tablets, they do have small voids, but these are mostly spherical, and whereas those from the direct mixture are quite large cracks. These tablets were characterized at Napoleon BASF, and it was found that the disintegration time, which correlates to the dissolution time, is much shorter for the direct mixture and much longer for the Colatab, as you would expect. And also the hardness is different. So all of this is really influencing the dissolution properties of the tablets themselves. And it turns out that if you try to package these or handle these, the direct mixture tablets, they can essentially fall right apart. I asked the question, well, how much porosity is there in that case? So we can easily segment each of the different phases in this image. And what we find is the porosity for tablets is on order from 3 to 4% on average. So that's a characterization of excipient all the way to tablet form. How might we do things differently? Let's say if we wanted to look at a device. So for this case, I use this sterile eyedropper bottle. So this is an over-the-counter preservative-free eye solution. It's marketed to have a one-way flow valve for the liquid, which is important because it doesn't have preservative. You don't want anything to get back into the bottle. And basically, there's a mechanism for any return air to go through a silicon filter. So I wanted to understand exactly how that works in this case. So data were collected, and here is a 3D volume. And on the right side is a 2D cross-section in that case, of the sample. And you see that there's a very complex mechanism up top. And in this case, we're not going to use voxel assignments. What we have to do instead is use subvoxel surface determination. So what does that mean? Well, if we zoom in on one 2D cross-section, we see the voxel space. And what we can do is we can use a program that segments data using surface determination, where it essentially cuts through voxels to allow you to have smooth surfaces with subvoxel resolution of these. And that's ideal, especially if you want to compare this back to CAD drawings or compare across production pieces. So that was done in this case. So what was done is that the entire volume was segmented from those internal bright features, which were highlighted in orange on the top and blue on the bottom, and we can calculate a wall thickness of that. And what we notice is that there's a groove that's happening right here. There's a gap separation and some stuff going on in top. And if we open that, we can explain exactly how they're able to let the liquid out, but not let any airflow back in. So basically that groove is right here. If you turn the bottle upside down and squeeze, it allows this space in here to be filled by the liquid. And that applies upward pressure on this top part. And as you press harder, it fills all the liquid space and floods all of this and lets it out. When the pressure is released, everything comes back down. And there's a space off to the side that's in a different cross-section that it has to go through a filter to get back in, that's located down here in the bottom. So that can easily be explained. And if the manufacturer is curious, they can use computational tools, for example, to look at fixture and deformation simulations. So basically, as you apply pressure, there are tools to do nominal to actual comparison, let's say, to verify that each of the parts are being made uniformly. You can do structural mechanics simulations for other devices, maybe titanium rods that might fit as bone or replacements of bone. You can also do disintegration and dissolution simulations of your tablets with some programs. And we talked about that with an expert from DigiM and how that's done. And I is going to put a link to that in the chat. So basically, CT can be a very powerful tool. And I hope by watching this, I've convinced you that it is a good tool to provide non-destructive imaging of pharmaceutical materials and products. I hope you see how it can be quantitative. And there are different approaches how to extract quantitative information depending on what you're imaging. And we looked at a couple of examples showing X-ray CT used for solid dosage forms and a small device dropper. And with that, I'll break and make a break for time for any questions.
Yeah, I think, Angela, we have time for probably one more question before we should move on.
Okay.
And this is regarding like a predictive modeling. You mentioned disintegration simulation with after speaking with the DGM people, but have you thought about doing porosity related to hardness and then maybe like a predictive model of disintegration? I mean, the reason I bring this up is if disintegration is one of your main lot release QA tests, you don't want to fail that. If you can predict that you're going to fail it, then you don't have to do it. So that is a huge cost saving. So have you thought about doing those?
Absolutely, and that is done. So because we're in lieu of time, we didn't have time to talk about a lot of the characterization that is done for both for the powder that's even before it's formed into tablets that can make some predictions about how well it'll be, how well it will form tablets. So and there are many scores that powder is given, but of course you need to make the tablets and then test and confirm all of this. And there are a number of laboratory tests that are done to evaluate that, and CET is just one of those.
Okay, that's great. Thanks, Angela. No more questions at this time.
Okay, so I'm going to stop sharing my screen. And next, that will give time for Suzanne to set up for the second half.
All right. Thank you, Angela. And if anyone has any questions for her, you can directly email her. I just put her email address in the chat. So next session is going to be about QC.
Hello.
Ready? Yeah. Sorry, go ahead.
Sorry. Welcome to the second part of this talk in this series. My name is Suzanne Schreyer, and I'm the senior scientist for the Raman analytical devices. And my talk will focus on real-time pharmaceutical quality analysis and control using a handheld Raman spectrometer. So we're going into the world of molecular spectroscopy at this point, and we're also going to the world of portable instrumentation. Okay. So before we start, we're going to basically go through some fundamentals of Raman spectroscopy, and we're going to talk about how that's significant for handheld Raman. I'm also going to cover a few applications for handheld Raman and some examples in the pharma workflow. In particular, I'm going to talk about polymorph identification as a case study approach. Okay. And before we start, we have a polling question.
Okay, so let me start the second polling question. Okay. So what we wanted to ask the audience for this part of the webinar is, how familiar are you with handheld Raman spectroscopy? So you might say you're very familiar and I use it regularly, or somewhat familiar. I've seen demonstration or read about it, or you've heard of it but never used it, or you might say not familiar at all. So answers are coming in fast. I'm going to give you a few more seconds. Okay, then I'm going to close the polling in 3, 2, 1. Okay, let me share the results. So 38% of the audience said somewhat familiar, 13% very familiar, then about quarter heard of it but not familiar at all, and a quarter each.
That's
Okay.
great. That's quite a spread of responses. Yes. Yeah.
Okay, I'm going to stop sharing and back to you, Suzanne.
Okay, thank you. So for those people who are kind of familiar with it or have heard about it, I'm just going to talk a little bit about the fundamentals of Raman spectroscopy before we get started. So what is Raman spectroscopy? Well, Raman spectroscopy first observed in the 1920s by C.V. Raman, who won a Nobel Prize for this. And at that time, his instrument took all day to basically using natural light to shine on a sample. And Raman spectrum was the result of the light hitting the actual molecule. Okay. As it hit the molecule, it undergoes something called elastic and inelastic scattering, and that produces a spectrum. And each molecule has a very unique and characteristic spectrum. So this makes this a selective technique. Okay. Now, in this case, this cartoon basically goes through what is happening within the actual system as it's going through. So what we have here is we have light shining onto a sample, okay, and most of that light is scattered out. This is called Rayleigh scattering. It's just like a mirror effect. It all scatters out and is lost. But about 1% of the time, or sorry, about 1 in a million of the time, a molecule is actually interacting with that incident light or that incident energy. And if it does, it's called Raman scattering. And Raman scattering is an inelastic technique. And if the energy of the incoming photon is not equal to the energy of the scattered photon, then you can either get a Stokes effect, which is a redshift, or you can get an anti-Stokes effect, which is shown here as a blue shift. Okay. In either way, the energy of the scattering, and the one we're interested in is when the energy of the scattering is less than the energy of the incident light, which is the Stokes effect. And this will produce what's known as a Raman spectrum. So Raman spectrum is shown here. We have the Raman shift. So basically you can assume that there's a big Rayleigh filter line that's set up here to filter out anything that's just elastically scattered. And here what we're seeing is the result along the Raman shift line of what the resulting peaks are. So as you shine energy onto a molecule, it either does a stretch, it does a bend, it does a waggle, and each of those has a characteristic point or a frequency. So if we look at a Raman spectrum, and for those people who have ever looked at an FTIR spectrum, very similar type of results. If you're looking at a certain frequency range, you're going to see, in this case, around 1,000, you're going to see the ring going waggle. If you look towards the far end, or you can see the amide shifts. And if you look at the first, from about 200 up to 900, you're going to see a CH bend. So putting all of these components and peaks together, rather like a jigsaw, you get what's called a fingerprint, or a very characteristic spectrum for a molecule. And once you get that very characteristic peaks for the molecule, you can then analyze whatever the material is. So the caveat, of course, is that it is Raman active. Anything that's Raman active has a carbon, hydrogen, oxygen, nitrogen that is covalently bonded. So that, fortunately, fits most of the APIs and excipients that are present in pharmaceuticals. And that's why this technique is very useful for the pharmaceutical workflow, for characterizing your incoming materials, and for QA and QC of your molecules, of your drugs. So what are some of these benefits? Well, the nice thing about Raman is it requires little or no sample preparation. If you have a bottle, if you have a drum, as long as you can see a sample inside, you can scan it. You don't have to open anything up. Okay. It also is a non-destructive technique. So when we can scan through the container and analyze what's in there, we hope none of this material will be destroyed or changed in any way. And we have the ability to scan anything like solids, liquids, powders, pastes, and gels. For portable systems, in this case, we do not do gases, but we can do any kind of other kind of material. And we can also, because we utilize a 1064 nanometer laser, we have the ability to scan colored materials, and we can also scan through colored containers. So that's some of the quick advantages of Raman spectroscopy for the portable workflow. Okay. So how does this actually work? So let's look at a cartoon of how our portable system works. So we start off with, so this is a little cartoon of our instrument. We have a sample that's held against the nose cone, okay, like so. We scan the laser into the sample. It traces a diffuse reflectance path through that sample, and then that will come back into the detector. Like I said, most of the light will be scattered out, but about 1 in a million of those photons will react with that molecule, cause a stretch or a bend, and that will send that energy back into the detector, where we can analyze it, produce a spectrum, and then compare it with an internal library of, in our case, 13,000 materials to see if there's a match. And if there's a match, you get identification. In this case, right on the screen, you'll see the results of the identification. And all of this is done usually in about 30 to 40 seconds. So this has the exact result of giving a really fast result that's easy for any non-scientist to operate. Okay? Once your admin has put in the library materials and have set it up, you can just hand it off to your operator wherever, either in the warehouse floor or on the process line, and they can quickly operate it and then clear your materials or get a result, like I said, in about 30 to 40 seconds. We also have an onboard scanner and camera, so you can do barcodes, and you can also take pictures of your materials if you need to. And all of this comes together in a data stream that's 21 CFR Part 11 compliant, and you can get the data out if you want and analyze it further in other software, or you can just use it to do a quick pass-fail for your incoming materials. And here's some example of what it actually looks like. You can run a quick check of your material, and it'll tell you, yes, this is what the material is supposed to be. Or if you think you're worried about adulteration or any kind of counterfeit materials, then it will tell you if you fail to find what the material is supposed to be. And like I said, that all the data comes out in a PDF report and a data stream, so that you can quickly analyze and sign for your materials. Okay. Because it is used in the pharma workflow, there is a complete regulatory acceptance for the handheld Raman. So there are a number of monographs that we are compliant with. First of all, we're compliant with the USP, so and the EP 2248, and also the Japanese Pharmacopoeia. And what you'll see is when we set up the instrument, or when we usually come in and make sure that we're compliant with all of these by doing an IQ, OQ, PQ, and we'll also check that you're compliant with the 21 CFR Part 11, which is the data integrity compliance. Okay, so we'll make sure that every instrument will undergo the complete testing to find out that they are compliant with all of these monographs. Just as a point of reference, because this is a handheld portable instrument, the compliance is focused on qualitative measurements. So this instrument is not quantitative, but you can use it for screening or for verification purposes. And before we get into some of these examples, are there any questions?
Yes, Suzanne, we have a question coming in. So does the material need to be homogeneous or can it be mixed?
Oh, good question. Yes, it can be both. So the instrument has a couple of modes. It will look for a pure material if you have it in straightforward RMID mode, or if you're using it on a process line or QA/QC, it will also find up to 5 components of a mixture. Okay.
Okay, that's great. Thanks. And a slightly longer question. I think we have time. So you mentioned that the Raman fingerprint was very specific to the vibrational frequencies of the molecule itself. So it's a molecular fingerprint. So how does that change depending on the solid state form of that molecule? And then would you have to retrain your matching libraries to recognize individual solid forms of a specific molecule?
That is actually a good question, and it leads into the next part when we're talking a little bit about the difference in the solid forms. For example, for polymorphs, Raman is very good at finding different polymorphs because they have different crystal pack sizes, so they pack differently, and Raman tends to be sensitive to that. However, there is kind of a range for that. There's a lot of materials that if we can see a difference in the spectra for that crystal form, then yes, fine. But if it's lower than the resolution of the instrument, we won't be able to differentiate that. So that's very material specific.
Okay, that's great. Thank you very much. No more questions at this time, Suzanne.
Okay. So let's go on to some applications that we are interested here. So you can see actually how it works. So where is Raman basically used? Well, straightforward, right off the top, it's mostly used in raw material identification. It's very useful for that. You can quickly scan your materials and find out whether you're verifying what your material is. You can scan your incoming materials to make sure that you're getting what you're supposed to. You can scan for excipients, for nutraceuticals, for APIs. Okay. Where also it can be used and it's very useful, is for verification purposes. And this would be more in the QA/QC lab, where you want to make sure that your materials are consistent and what you want to go into your formulation. So you can look at chemical solvents, excipients. There's some other examples of cell culture media. You can look at finished products and make sure that all the way along the process line, from raw material inspection all the way through to QA/QC, you have what you're supposed to have. Okay. The other one you can use it at is actually authentication. So you can check for brand security. You can check if you have a counterfeit material, or if any of your customers sent in a product that they think is there's something wrong with it, you can scan that material as it comes in and compare it to your retained samples, and to make sure that everything is okay. So there's it can be used throughout the entire process. If we just look at it from the traditional RMID workflow and where it would fit in here, this is a traditional RMID workflow. So this is before you use the handheld instrument. So in that traditional workflow, it's a multi-step, and it can be time costly as well, because you would need to identify what the material is from its label. Then you would have to quarantine it and open it up. Take a sample out, send it to your lab, and wait for them to actually run it on their bench instruments, make sure that this is what it's supposed to be, and then they come back to you to the warehouse and say, okay, you can release the materials from the quarantine and put them into the process. This can take time. It can take days. Sometimes depends on the backlog of your lab. Conversely, if you use a handheld Raman as part of that workflow, then the material comes in. The operator basically just scans the material. Like I said, it takes 30 to 40 seconds to scan each incoming material. The instrument will tell you it's a match or it passes what it's supposed to be. So, and then you just release it into the out of the warehouse and into the entire process. So instead of days, you can do it in minutes. Very fast, very efficient. Okay. Less movement, less chance of contamination, and overall, it comes down to a lower cost per analysis. Okay. And at this point, I think we're stopping for polling question number 2.
Okay. So let me start. This is going to be the last question we have for the audience. Okay. So the question is, what is your budget? What is your biggest challenge with implementing new analytical technologies like handheld Raman? Okay, so here are your choices: regulatory compliance or validation, or integration into existing workflows, cost and return on investment concerns, lack of training or expertise, or not sure where it fits in our process. I was thinking about budget before this meeting, and that's what the biggest budget came out. Okay, so the answers are coming in. Actually, it's pretty evenly distributed.
Yeah, no one seems to be concerned about integration, though.
No,
That's
or
surprising.
workflows.
Yeah. Well, that's interesting. Cool.
Okay, so I'm going to give you a few more seconds. And I'm going to close the polling in 3, 2, 1. I'm going to end the polling and share the results. Yeah, so as Simon said, nobody chose integration or workflows, but about 33% regulatory compliance validation, and 20% cost and return on the investment concerns, or not sure where it fits. And 17% of the audience said lack of a training or expertise.
That's it.
Someone said it's hard to pick just one. So
it's true. Well, and all of these, it's going to be up to the QA/QC people to kind of do all the hard work and put it into the system, because once it's in the system, it's super fast and seamless, but there's always regulatory compliance and integration beforehand. Okay. Well, thank you. So we'll go on. I'll show a couple of some examples of where it can be used in the workflow, and and how it can help in the workflow. Let's say. So the first one would be pretty well in the QA/QC environment. Here we have a spectra of most common excipients that you would see that would come into a QA/QC lab. And what has happened here is that the QA/QC person has gotten the samples, certified samples, and they scanned them on the Raman instrument, and they got characteristic spectra. They've been able to then do challenge materials, figure out how to build their library up so that they can differentiate all these materials. And that was fine, but you can see that they've also were concerned about different states of these materials. So we have calcium phosphate anhydrous and calcium phosphate dihydrate. And they want to be able to differentiate those types of forms. And from the work that they have done on this, they were able to say that, yes, we can differentiate these two different types of forms, which is very good, because you don't want to add the wrong material to your mix at the end. So for QA/QC, building up a library saying, yes, this we can clearly differentiate all these materials. We have selectivity on the type of materials. That is important. We can also use this as part of a monitoring of a process. So in this case, this is just a little schematic of we have two starting materials, an epichlorohydrin and a methoxyphenol, and they're used to make a ritonavir intermediate. And during the process, we want to see the epichlorohydrin and the methoxyphenol decrease. So what will happen is the green and the orange peaks should gradually decrease, and you'll see an increase in the peak size for the ritonavir intermediate. So you can take samples at line or offline and monitor where in the process you are, and so you're not overmixing or undermixing at this point. So that's an example of how you could use this in the process line. And another one that was important for us is that authentication. And in this case, I have an example of something that was near and dear to our hearts a little while ago. What's in this sanitizer sample? Like, is it actually what it's supposed to be? Is it going to work properly? So, and of course, that there was a lot of contamination of consumer products, especially for an ethanol-based hand sanitizers. They were adding in methanol, and methanol, of course, is a health hazard, and it also decreases the efficiency of the actual hand sanitizer. So, besides being an efficacy and a safety issue, we were interested in, can we use Raman spectra to verify that the material is what it's supposed to be? And in this case, the answer, of course, was yes. Is if you look at the spectra of hand sanitizer, which is in blue, and a contaminated sample, which is in red, you'll see, especially here, there's a large shift in this peak and a small shift here. And that difference was enough for our instrument to say, yeah, this fails. This is not a pure ethanol hand sanitizer. This is a contaminated brand. So you can just toss it out, and because that's not what we're interested in. So this is a good example of how to use it for authentication and counterfeit analysis. Okay, and the last study I want to look at is the polymorph identification. So polymorphs are quite big in pharma products. Polymorphs will impact physical properties. So you need to know what type of polymorph you have in your mixture, because it will affect the dissolution rate, the bioavailability, the safety, and it will impact your entire process if you get the wrong polymorph, as well as impact the efficacy of the final product. So Raman tends to be very sensitive to spectral changes as long as it's within the resolution window of the instrument. So as the crystals change, the packing of the crystals will also change, and that will impact into the actual spectra. I'm going to show you some examples of how that changes, how the polymorph form changes depending on what the crystals is. In this case, this is for a coating material. Titanium oxide is a very common coating material. And if we look at the polymorph forms, we have three common polymorph forms. Two of the most common are the anatase and the rutile. The top spectra shows the anatase and the rutile form as taken on our instrument, and it's obvious that there's quite a big difference. And in fact, David Tuchel characterized the most common peaks that are present in both types that are shown here. And you can clearly see that depending on which one you want, you can differentiate it selectively from the other one. Another example, this is for an active ingredient. This is for ritonavir, a very large molecule here. It's used as part of a cocktail to treat HIV. So it's extremely important that you get a correct polymorph, because if the cocktail will not be as effective if you use the wrong material. because ritonavir tends to act as a booster for the other materials that are in this cocktail. So if you have the wrong polymorph, it can affect the solubility, it can affect the bioavailability of your final product. And so it can put people at risk who have HIV. There was a previous study then that showed that there was an incorrect polymorph form of ritonavir that was in a cocktail, and the medications had to be withdrawn due to its incorrect form. So you want to make sure you have the correct one. In this case, the correct polymorph forms are very easily visible on a Raman spectra. In this case, we're specifically looking at the aromatic ring bend here, and there's a CN stretch, CH bend, and there's an amide stretch that's over at this end. And if you compare the polymorph types between the three different polymorphs that are out there, you can see here that they have enough of a difference in this cartoon schematic that I actually I had OpenAI actually generate this for me, that you can see shifts in all the significant peak areas that will be able to differentiate the different types. So form B, form number 1, is the marketed form. That's the form that they're looking for. There's 2 other common forms in green and in red that have different types of packing. One, for example, the green one, form 2, has stronger hydrogen bonds, so it tends to have a tighter pack, and a red has a different type of hydrogen bonding, and so you tend to get a shift in the C double bond O stretch. Okay? So in any case, if you set a certain cutoff threshold, you'll be able to selectively separate out the forms and make sure in your formulation that you have the correct form. And if anyone's interested, there's some more literature available on this, talking about ritonavir polymorph forms. Okay. And that's coming to the end of the talk. I just hope I've told you enough about handheld Raman and Pharma that you can see where it can fit into your pharma workflow, from the 100% inspection of incoming materials and then going beyond the raw material identification to maybe monitor a reaction or verify our finished formulation, check for counterfeits, or let's do selectivity checks of your retained samples and in QA and QC. Okay? So hopefully we showed you how well it can fit into your workflow aside from just our raw material ID. And I want to thank you for your attention. And if you have any questions, I'd be happy to answer them.
Well, Suzanne, we have a lot of questions and we have almost zero time to answer them in. I mean, any questions we don't get to, we'll handle through email. Let me just pick one. Hopefully this one is not too complicated. But the question is, how are polymorphs in a prepared drug evaluated? And can the results be optimized? I guess they're indicating maybe some sort of quantitative or ratio between different polymorphs. I'm not sure.
Yeah, so we can differentiate which polymorph it is. If you have 2 polymorphs of a certain drug, you can add both of those to your library, and if there's enough of a separation between the 2 of them in the spectra, then you can clearly separate out the 2 types. In terms of quantity, no, because this is a portable instrument, so we're strictly verification, screening, qualitative analysis.
That's awesome. Thanks. We really have no more time for more questions. So thank you again, Suzanne.
Thank you.
So as I said earlier, a recording of the webinar will be available tomorrow, and an email will go out to all registrants. And the link to all the resources I put in the chat, they will be available on the same page too. And we covered single crystal thermal analysis, powder XRD, EDXRF, CT, and handheld Raman analysis techniques in this webinar series. And this one will conclude the series. But one of the techniques we briefly mentioned but didn't go deep into is the electron diffraction. And in a different webinar series, our co-presenter Simon gave an in-depth look into how electron diffraction, or micro-ED, people call it different names, but is solving very tough problems for the pharmaceutical industry. If you're interested, you can watch the recording now. I'm gonna put the link to the recording page in the chat too. So if you are interested in it, please take a look. Okay, well, thank you everyone for joining us, and we'll hope to see you at the next webinar series.
That's great. Thank you. Bye.
Bye, everyone.
Thank you. Bye.